Hello everyone, and welcome back to Comm 215 Business Statistics. Before we get started, we'd like to thank you for your continued support on our Facebook page. So as promised, we're now about to deliver part 2 of the Comm 215 midterm review, which is the problem solving part. So without further ado, let's get started with the box plot problem. As part of an operations study, a bank operations analyst observed the length of time in minutes to complete a transaction for a random sample of 40 customer transactions last month. And then we have the data, so we have our 40 data points, and then they're asking us for 4 elements. The first one is to construct the stem and leaf diagram. The second one is to compute the 5 numbers required to construct the box plot. So those are the 5-point summary, also called the 5-star points. The third part is to construct the actual box plot and identify any outliers if applicable. And finally, to comment on the shape, or otherwise known as the skewness, of the data set. So let's go ahead and do one thing that is very crucial that I talked about in the theoretical portion, which is order your data. Okay, this is a little bit tedious, but it's really going to come in handy as you solve these problems. So always, whenever you have data set at the top, just get into the habit of ordering it. That way it'll make finding the median, the min, the max, everything so much easier. Okay, so let's go ahead and do that. Now feel free to fast forward to where I'm done ordering the data. All right. Wonderful. So we are all done. Now, one thing I suggest that you do once you're done, like I said, I know this is a bit tedious, but you're going to get much faster at doing this the more problems you practice with. So now what we're going to do is we're just going to cross-check with the data at the top to make sure that we didn't forget anything. So you see, we forgot one. We forgot 7.9, so let's go ahead and add that right here, 7.9, which is right here. And let's keep going. So then we're just missing 2, so 9.5 and 9.7. So it was just a little mistake. Instead of the 8.0, I apologize for that. So 9.5 and 9.7. Awesome. So we're good to go now that they're all ordered. So when building your stem and leaf display, this is the stem right here. Now on the left-hand side, we're going to have the different branches, if you will. So we know that because our numbers are ordered, see how easy this is, we know that the smallest possible number is a 0 and the biggest will be a 9, right? So for the branches, so we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way until 9. Okay, we know that those will be our branches. And now we're going to fill in for the leaves on the right hand side. Okay, so I'm just going to put this here for you to remember. So these are the branches, which are all the categories, if you will, on the left-hand side. And on the right-hand side, you're going to have all of your leaves, which are going to be filled in with all the data, right? Now, the first number is 0.2, right? So because my branch is a 0, I'm going to put a 2 right there, right? Now, the way the stem and leaf works, and I want you to follow this closely, if I take this number and I simply extract it from the stem and leaf, I'm going to get 0.2, right? Just plain and simple. If I take this number out, it's 0.2. So then, in order to find the leaf unit, what you have to ask yourself is, what do I have to multiply 0.2 by in order to get what's in the data set, which is 0.2, okay? So remember, you extract the number straight out of the stem and leaf, just 0.2, and then what do I have to multiply this number by in order to get the actual data point, which is 0.2? So in this case, it would be times 0.1, and this would give me 0.2. So notice how this is my actual data point. This right here is simply extracted directly from the stem and leaf. And this right here, so the in between, what you're going to multiply by is going to be your leaf unit, okay? We're going to do a couple of these and you'll see it's going to become second nature, okay? So now we have our leaf unit. So we're going to put our leaf unit over here to remember, and we're going to do the exercise 1 or 2 more times in order for it to really sink in. So we know that the next number is going to be 0.4. So I'm going to put a 4 here. You don't have to put the commas if you don't want to. You can literally just line them up one after the other. I think it's a bit cleaner, but it's entirely up to you. So once again, let's retry the exercise. If we extract the number from the stem and leaf as is, so we get 0.4, right? But we know that the actual value is 0.4. So you have to ask yourself, by what do I have to multiply this to get my actual data point? And that is your leaf unit, okay? Now, for those of you that are more comfortable, you can obviously do it the other way around, meaning that you can take your actual number and then ask yourself, by what do I have to divide it by in order to just be able to put 0.4 in the stem and leaf, okay? I think this way is easier, but it's really entirely up to you. So then let's just fill it in for the rest of the stem and leaf, and feel free to fast forward to the point where I'm done. So we're all done. So this is what your stem and leaf will look like. You literally simply put in for all the branches, you add in all the different data points, and then this is pretty much how you build your stem and leaf. So this is question A. Now, one thing I want to point out, because they do ask you to comment on the shape of the data set in part D, there's 2 ways that you can comment on the shape of the data set. We're going to do it a little bit later once we do the box plot, but you can also do it right now as you do the stem and leaf. So I'll show you what I mean by that. Notice how the data goes like this, right? So this quite simply means that if we were to flip it vertically, what we would get, so let's just put a line right here, just to give you an idea. You can see that the data set is right skewed or positively skewed, okay? Notice how the arrow is going towards the right. So once again, just pretend that it's flipped over as if you were to see the bell-shaped curve on its bottom. And you can clearly see that it is right skewed, right? Now remember the other trick that I told you to be able to tell whether it's right or left skewed? And that is where the median and the mean fall, right? So we're going to compute that in just a second because we need it for part D, but we'll be able to double check whether our analysis in part A of the shape corresponds to what we're going to do to the box plot and corresponds to the mean and median theory, okay? So what would happen here is that the median is going to be smaller than the mean. Perfect. So this is just I'm showing you the stem and leaf skewness just because it's an extra way to triple check that your data is okay. That your skewness, reasoning is good. So now let's move on to question B, where we're going to compute the 5 numbers required to construct the box plot. What are those 5 numbers? So I'm going to put them right here in the top. This is either called the 5-number summary, the 5-point summary, or sometimes actually I should say, you'll see the 5 star points for the box plot. So what is the 5-number summary? So the first thing is the smallest value. The second thing is the largest value. so the max and min pretty much. The third element is Q1, your first quartile. The fourth is Q3, your third quartile. And the fifth is the median. So in a midterm, when they ask you for the 5-point summary, these are the 5 things they want. Because from these 5 points, you can deduce pretty much anything else needed to compute and to draw your box plot, okay? So the reason why there's no IQR here, I get asked this sometimes, is because with Q1 and Q3, you can easily deduce the IQR. So there's no need for that. Really, the essential things are max, min, Q1, Q2, Q3, all right? So let's go ahead and compute for those values. So the first one, the min, is quite simple. We have it right here. Our data is ordered. This is super fast. It's 0.2. The second point, once again, fairly simple. Our data is ordered. No way we can make a mistake. 9.7. Then we have our Q1. So our first quartile. So we know that there are 2 things when finding the quartiles that we need. The first is the positioning of the value. And then once we have the positioning, depending on whether it's an even or an odd number, we will either round up or take the average in order to determine the value. Okay, so let's start with step A. Let's find the position. So first quartile, we know that's 25%. So the position is found by doing 0.25 times the sample size, which here will equal 0.25 times 40, which is equal to 10. So that's the position of my value. Now, because it's an even number, in order to determine the value, I'm going to have to take the average of the 10th and 11th position. Okay, so once again, my data is ordered. This makes it very easy to do. Let's go ahead and select those 2 values. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 10 right here and 11 right here. So I'm going to take the average of those 2. So it's going to be 1.4 plus 1.5 divided by 2. So this is 2.9, I apologize. So this is going to be 1.45. Okay, so that is my first quartile value right here. So let's repeat the process for Q2 and Q3. So I'm just going to write it out up here. Q1 is equal to 1.45. And I'm going to repeat the process below here for the other ones, okay? So let's remove this. Let's do the second quartile. So we know the position is 0.5. 50% is the middle. So here also, 0.5 times 40, that's 20. So once again, it's an even number. So it's going to be the average of the 20th and the 21st position. So let's go get those now with the orange right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that would be the average of 2.9 and 3.1. So let's just erase this right, oops. Sorry about that, right here. All right, so it's going to be the average of 2.9 plus 3.1, so that gives us 6. So my median is 3. So let's go ahead and put it right here. So Q2, which is equal to the median, is equal to 3. And let's go ahead and find the final quartile, which is the third quartile. So we know that that is 75%. So 75 times, whoopsie daisies, 75 times 40 is 30. So once again, because it's an even number, it's going to be the average of the 30th and the 31st position. So let's go ahead and find those. Let's single them out with the red. So we were at 20 over here. So 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So it's going to be the average of 5.5 and 5.6. So let's go ahead and fill those in right here. So 5.5 plus 5.6. So this gives us a total of 5.55. So I'm going to go ahead and put that up here. So my Q3 is a total of 5.55. All right. So now that we have our 5-point summary, we can go ahead and start drawing our box plot. So we're going to move right on to question C, which is construct the box plot and determine if there are any outliers. Okay, so let's go ahead and do that. Now, before we draw the box plot, there's one more thing that we know that we're going to need anyways, so we might as well just compute it ahead of time and then simply move on to just drawing the box plot. So it's not part of the 5-point summary, but it's easily deduced. The interquartile range, which we know to be the difference between Q3 and Q1. So that's simply 5.55 minus 1.45. So that gives us a total of 4.1. Now there's one more thing that I was just adding to the IQR, in addition to the 5-point summary, that you will need prior to drawing your box plot. It'll just make your life a lot easier, and that is the upper and the lower fence. So let's go ahead and compute those two. So the upper fence, we all know, is the fence that's going to be on the right-hand side. So it's going to be Q3. Okay, it's always the quartile that's closest to that fence. And in this case, since we're moving further towards the right, we're going to add 1.5 times the IQR. So this is going to give us a total of 5.55 plus 1.5 multiplied by 4.1. So this is going to give us a total of 11.7. So that's my upper fence. Now let's do the same thing for the lower fence. So it's going to be the fence on the left-hand side. So the closest quartile is Q1. And since we're moving further towards the left from Q1, we're going to subtract. And we're going to subtract the same thing, which is 1.5 times the IQR. So this is going to give us a total of 1.45 minus 6.15, which is 1.5 times the IQR. And this is going to give us a total of negative 4.7. Okay, so now that we have our two fences, our IQR, our three quartiles that are essential, our max and our min, we can go ahead and draw our box plot. Because we have our upper and lower fence, we can easily determine the unit scale that we want to use for a box plot, right? So over here, we're going to go as low as -5, since our lower fence is at -4.7. And up here, we're going to go as high as possibly 12, 13. So let's go ahead and fill these up. Wonderful. Okay, so we went a little bit overboard. That's fine. Perfect. So the first thing that I suggest you put in is your median, always. So the median is here at 3. So this is my median, or my Q2. Next, I suggest we do Q1 and Q3. So Q3 is approximately over here at 5.55. And Q1 is approximately here at 1.45. Okay, so we have our Q1 and our Q3. Perfect. So now we have our box. Next, I suggest we add our upper and lower fence. So the upper fence is all the way up here at 11.7. And the lower fence is all the way down here at negative 4.7. Okay? Now, I often get asked, until where do the whiskers go? The whiskers go, and this is important, so pay attention. The whiskers go until the last data set before you reach the fence. So what do I mean by that? I know that my upper fence here is at 11.7. What is the last data set before hitting the fence? It's going to be my last data set, which is 9.7, right? So right over here at 9.7, my whiskers are going to go until there. So let's just go ahead and draw these. And this is because my last data set here is at 9.7, okay? So on the left-hand side, we do the same thing. Our whiskers are going to go until the last data set before we hit the fence. So here it's going to be until 0.2, which is, let's say, right around here. So my whiskers are going to go until here, okay, at 0.2. Now, it asks us to find if there are any outliers. How do we determine if there are outliers? So this is where the whiskers come into play. Let's say, hypothetically, okay, it's not part of the problem, but let's pretend that we had another data point here at 13, okay? Outliers are determined by any point within the data set that goes beyond the upper or lower fence. So your whisker is the last data set before hitting the fence, which in this case would be 9.7. And then the next data point, 13, would fall over here, and that would be an outlier, okay? So I repeat that. The whiskers go until the last data point before you hit the fence, and anything beyond that, so any data points beyond the whisker data point is an outlier because it falls outside the fence, right? Same thing for the left-hand side. Okay, so one last time. The whiskers go until the last data point before you hit the fence, and anything beyond that is an outlier. So in this case, are there any outliers? No, there are not. Everything is within the two fences. And finally, they're asking us to comment on the shape of the skewness of the data set. Now, the reason why earlier in the stem and leaf I drew the curve is so you could really see that it was right skewed, because here it's a little bit more difficult. Why? Because you can't, if you trace the shape, most of you will have the just intuition to trace it going this way and then going down like this. I'll draw it here and then I'll erase it real quick just to show you. So most of you will want to go like this, whereas we know that that's wrong because we know it's right hand skewed. So what I suggest you follow more is what I taught you before, which was the mean and the median trick. So you know that if it's right skewed, it's because the median is smaller than the mean, right? Now, how do you tell that by the box plot? It's quite simple. We know that our data is mostly concentrated on the higher end. Okay, notice how within the box plot, it takes up this huge portion, the higher end values. So what does that mean? We know that the mean is a data point that is sensitive to extreme values, meaning that it's going to skew the mean, right? The more we have values that are further at the extremes, whether on the lower or the higher end, it's going to skew the mean. Now here we can see that the higher concentration of values is right here on the higher end. So that means that if my median is at 3, the mean is going to be higher up as it's being pulled by that 7.9, that 9.5, and that 9.7. So it's going to be skewed towards the right. And because of that, we know that the mean is going to be greater than the median, which you can see right here. And so we can tell that it's going to be right skewed. If it was a perfectly distributed bell-shaped curve, we know that the mean equals the median. And what would you see in the box plot? You would see a perfectly even box plot. So the mean and the whiskers would be, and the quartiles, everything would be perfectly distributed. So you would have the same length between the Q1 and the mean and the median, and between the median and Q3, and the whiskers would be identical. But this is not the case here, as you can see. And so the graph for a left skewed box plot would be the other way around. You would have a higher concentration of data on the left-hand side, pulling the data towards the left, right? And so that's it for the box plot question. Stay tuned, and we're going to solve some probability problems next. So now let's do a probability problem. The coming year is expected to be a good one for your company with a probability of 65%. Given that it is a good year, you expect that a dividend will be declared with a probability of 80%. However, if it is not a good year, then a dividend will occur with a probability of 15%. The one thing I suggest you do before you get started is always to break up the question into its mathematical form. And what I mean by that is, let's turn a problem that is in written form into simply equation form. And so let's just write out the probabilities that we have here, so we'll have them for the rest of the problem. So the probability of a good year, we have it right here. If it's the year is expected to be a good one for your company, the probability is 65, right? So the probability of a good year is 0.65. Then we have this little word right here, which is very key. We went over this in the theory. Given that it is a good year, you expect that a dividend will be declared with a probability of 80%. So what does this mean? This means that it's the probability of, and when I say to turn the problem into mathematical form, this is what I mean, okay? So we're going to write it out, because I know that if I give you the probabilities in this form, all of you can solve the problem very easily. It's when you read it in a context form that it's always harder to transform into its sort of number form. So we know that it's given, okay? Now, what is it given? Given that it is a good year, so we know that the condition always follows the bar here, right? So given this, which is a good year, what is the probability? So on the right-hand side is what I'm looking for, that a dividend will be declared. So we'll put DC for declared, okay? So given that it is a good year, what am I looking for? The probability that a dividend is declared, and this is 0.8, right? And then the next sentence, so this was the 0.8 right here. The next sentence, we have if it is not a good year. So the if and the given, I'll put them here, are the same, okay? If equals the given. So it means it's a condition, right? We're setting a condition. So let's write out this last one. So it's the probability of, if it is not a good year, what is the probability that a dividend will be declared? So a dividend declared, and this is equal to 0.15, right? Now, I'm just going to write out a little legend so we can keep it really simple. Let's put it over here on the side. Okay, I'm going to put it right here. So when a dividend is declared, we're going to call that D. A good year, we're going to call that Y. And a not good year, so not good year or bad year, we're going to call that, let's just call it B for bad year. Okay, so just so we don't have to write all this out when we solve the problem. right? So the first question is asking us. Now, notice how this is a lot easier. Before I get into the questions, notice how this is a lot easier, right? You have all your probabilities already mapped out, and then you simply need to solve for the questions, as opposed to going to get everything into the context form, which is always a bit tougher to extract. That's often the part that students struggle with the most, translating the text into just a simple probability form, okay? So once this is all done, notice how easy this is. And we literally did it step by step, guys. As you read the problem, write out what you see, okay? So we did given, we know that it's a conditional, that it's a good year, and then what are we looking for? That a dividend is declared. So we took it almost word by word and we put it in probability form. So now it's going to be very simple. So in part A, we want to know what is the probability that it is a good year and that a dividend is issued. So what is that? What we're looking for is the following. We want to know the probability that it is a good year, okay? So Y, let's refer to the legend here, good year, Y, and that a dividend is issued. So dividend declared is D. So this is what we're looking for. So once again, we literally took our context form and very slowly, as we read word by word, we wrote out what we were looking for. We want the probability that it is a good year, and so we know that that's the and right here, a dividend is issued, right? Now, what does this translate into? We know our rules, and we know that we can extract the and from the following rule. So I'm just going to do something very generic here. So we know that the probability of E1 given E2, if you refer back to the rules, is equal to probability of E1 and E2 divided by the probability of the condition, which in this case is E2, right? And you remember when we took this to the left-hand side to isolate for the and? Well, that's what we're about to do right here, okay? So we know that to isolate for the and, we need to take what we have right here, which is D given Y, multiplied by, the condition is going to be Y, so probability of a good year, right? So don't knock your head over this, okay? It should be simple. If you're racking your brain, it's because you're doing something wrong. So we have here D given Y, and the way we can isolate for the and is by multiplying by the condition, which is the Y here, right? Now remember the and, whether it's Y and D or D and Y, it's the same thing, right? And the and can be obtained in two ways. We could have either done this right here, or we could have done this right here, right? Same thing. We agree? To isolate for the and, it would be the same thing. But because we don't have this, we don't have the probability of a dividend being declared, and we don't have Y given D, we have D given Y, we're going to be smart and we're going to use what we have, okay? So this is going to equal 0.8 multiplied by 0.65, very simply, which is a total of 0.52, okay? So once again, we simply took our context form, put it in probability form, and then just solved very simply. So use what you have at your disposal. Don't rack your brain over this, even if the and can be solved in two different ways, okay? So now let's move on to part B. In part B, they tell us, what is the probability that a dividend is issued? So what is it that we're looking for? We agree that we're looking for the probability of a dividend being issued. So probability of D, right? So the probability of D is made out of two things. And what are those two things? It's a dividend and a good year plus a dividend and a bad year, right? We agree that the dividend is made up of these two things, because a dividend can only occur in this case in in two ways. A dividend can occur when it's a good year, and a dividend can occur when it's a bad year. And this is the probability of a dividend, right? So we need these two halves to form the full probability, because what do they have in common? The D right here and the dividend right here, right? So let's start with this one right here. Since we already have this one, we have it right here at the top in part A at 0.52, right? So we need to isolate for D and a bad year. So let's start with that. So the probability of dividend and a bad year is going to equal, now remember once again, from our rule, we're isolating for the and. So we're simply going to take the conditional multiplied by the condition. So we have it up here. So we have the probability of D given that it's a bad year. And we're going to multiply by the probability of a bad year. Now, how do we get the probability of a bad year? It's quite simple. We know that the probability of a good year is 0.65. So what's the complement of a good year? It's a bad year, right? So the probability of a bad year is going to be 1 minus 0.65, which is the probability of a good year. And we're going to multiply this by what we have up here, which is 0.15. So this is going to equal 0.15 times 0.35. And so the probability of a dividend and a bad year is going to equal 0.0525. And so then we're going to add it right here. So let's just remove these little arrows. Sorry about that. Alrighty. So then this is going to equal the probability of a dividend. This is from part A, so 0.52, plus what we just found here in our first one, so 0.0525. And this is going to equal 0.5725. So this would be the answer for part B. Probability of a dividend is issued. And finally, let's move on to part C. They want to know if a dividend is issued. Okay, so very important. If a dividend is issued, what is the probability that it is a good year? Okay, so let's write that out. So if a dividend is issued, what is the probability that it is a good year? Okay, see how simple that is? As you read the sentence, literally write it out. So this is what we're looking for. So this is equal to, we know that at the top, it's the and. And then at the bottom, be careful, it's the condition, okay? So it's the probability that a dividend is issued, dividend is declared, same thing. So then this and here, we have it from part A, it's 0.52. And then this here, we have it from part B, right here, it's 0.5725. And we simply divide through, and this is 0.983. Okay, and there you have it. So you see how simple it is? The hardest part, I know, is always extracting from the context to the simple probability form. But that's why I want you to get into the habit of really doing it step by step. As you read out the sentence, draw the bar for the condition. Draw what goes on the right-hand side, so what the condition is, and on the left-hand side, what it is that you're looking for. So this is always condition, and this is always what you're looking for given a certain condition, okay? This is what you want. All right? And if you do that, if you do it literally as you read the sentence, if you write it out word for word, so you have probability that a dividend is issued. So we're looking for the probability of a dividend being declared. So just probability of D. Or here, probability that it is a good year. And so learn to spot those keywords, the ands, the ifs, the givens. All these little things are what are going to cue you to writing it out in proper probability form. Okay. Alrighty, so now let's attempt binomial probability problem. And I really want you to be able to, after this problem, nuance the difference between a regular probability problem and a binomial probability problem, okay? So let's jump right in, and I'll point out some cues along the way. About 40% of all customers of XYZ charge card pay their bills in full before any interest charges are incurred. So that's the question. That's literally all we have. We have nothing else to go on. So let's, as always, what I'd like to do is let's transform the context into simple probability form. So what we have here is the probability of people who pay their bills before interest is incurred. And this is 0.4. Now that's literally all we have to go on, okay? So let's read the question now. Part A asks, in a random sample of 10 cardholders, estimate the number of customers who are expected to pay their account balances after interest charges are incurred. So what do we have? As we read the question, in a random sample of 10 cardholders, okay, all of a sudden here we have a new bit of information. So we have our sample size of 10, and then they want to know the expected number of customers who pay their account balances after interest charges are incurred. Okay, this is very important. After. So they want to know the expected of people who pay bills, so pay their account balances, after interest. Okay, so after they've incurred interest charges. So this is going to equal, what do we do now? It's very simple. Remember, I've always told you, if you're racking your brain over this, it's because you're doing something wrong. It should always be straightforward and go with the information that's available to you, okay? So we know here we have from the question, the probability of paying bills before interest. So it's very simple. To obtain the probability of people that pay bills after interest, we know that it's simply the complement, right? So the probability of those that pay bills after interest is simply the complement. So 1 minus 0.4. And so that's going to equals 0.6, right? Now, the expected number here can be obtained in different ways. Do you remember from the formula sheet? It can either be the sum of all the probabilities divided by n minus 1, or it can be, very simply, what do we have here? We know that we have the probability, and we know that we have a sample size, n times p, right? Remember, it should be very, very straightforward, okay? So the sample size, because we want the expected number of people that pay bills after interest, the probability should be that of what you would like to find, which is this right here. And so the probability is going to be the 0.6 and not the 0.4, okay? Very important. And then the n, well, that's simply 0.6 times my sample size of 10, right? So this is going to give me 6 people who are expected to pay their bills after interest is incurred. Okay, so once again, always keep in mind that what you're looking for, so the expected number of individuals that you're looking for, it should correspond to the probability that you're putting in. We use the 0.6 because we wanted after and the expected after interest. Okay, so very important. So that was the first part of the question. Now, a little tip. I suggest that when you solve for part of the question, you cancel it out. So you know you've done that, but then you still have a second part. What is the standard deviation Oftentimes, a lot of you, when solving questions in the midterm that have two parts within the same paragraph, you'll forget something. And it's just a silly way to lose points when if you cross it off, you can just move on to the second part because you know it still hasn't been crossed off. Okay? So in the second part, they want to know. So this was the first part. Now in the second part, they want to know what is the standard deviation. Now, if you remember from our formula sheet, since we're in a very binomial type setting here, we're using the n times p because all we have is the probability of one element and its complement. Okay, so binomial, remember, bi meaning there's only two outcomes, which is what we have here. So these are the little cues I'm talking about. Okay, you got to work with the information that you have. And so far, all that has been given to us is one outcome from which we deduced its complement. So now we only have two outcomes. That automatically classifies it as binomial. And in addition to that, we were given a sample size. When we're given a sample size and we only have two outcomes, that should light up a red light in your head. Boom, this is a binomial problem, okay? So the standard deviation for the binomial is simply the square root of n times p times q, okay? If you remember that from our theory portion. Side note, I don't want you to learn any of these formulas by heart. You will be given a formula sheet. Just make sure you understand them so you can use them when appropriate, okay? So this is very simple. We're simply going to plug in the numbers. So our standard deviation, now don't forget the square root, okay? It'd be silly to forget the square root, is simply going to be the square root So simply going to be the square root of 10, my sample size, times p, which is 0.6, times q, which is 0.4. Remember, p and q are complements. And so this is going to give us a standard deviation of 1.5491. 4 decimals is more than enough, okay? So that is our standard deviation. So now we can also cross off this second part and we know that we're done with this question, okay? So now part B, in a random sample of 10 card holders, stop right there. You know I like to break the problem up into very simple form. So n equals 10, boom, that's the first part. Estimate the probability that at least half of the expected number of customers pay their account balances before interest charges are incurred. So there's a few things here. The first thing is that we know that we want a probability. Okay, so we're going to be looking for the probability of something. That's number one. Okay, so I'm going to cross it off as I go. So I have this part of the question is good. I want to estimate a probability. That's good. That at least half, okay, at least we know is going to be greater than or equal to. Okay, now side note, all these little vocabulary cues you should know: greater than, at least, greater, more than, more, all these little verbal cues you should know, and you should know their mathematical symbol equivalent, okay? Now, greater than or equal to is not the same thing as greater than. At least, we know that it's the same thing as greater than or equal to. Okay, and why I say this is because it's very important not to forget the equal to, because that's going to make a difference. Okay, now we want at least half. Okay, so let's at least, and we want at least half of the expected number of customers. So what is our expected number of customers? So our expected number of customers that pay their account balances, oh, wait a minute, before interest charges are incurred. So another little thing here. Do we have this number? No, we don't. What did we calculate in part A? In part A, we calculated the expected number of customers that are expected to pay their bills after interest charges are incurred. So let's just go ahead and find that first, okay? So little part 1 here. And what we're looking for is the expected number of people that pay bills before interest is incurred, right? So this is going to be n times the appropriate probability. So here it's going to be 10 times, and the appropriate probability is the one of people paying bills before interest, so that's times 0.4. So this is going to equal 4 people. Now, for those of you that are a bit more comfortable with the theory, you know that in the same way that P and Q are complements, both the expected numbers would have been complements, right? So if we have 6 people out of 10 that pay bills after interest are incurred, then the complement, 10 minus 6, 4 people out of 10 will pay their bills before interest is incurred, right? Because they have to make up the entire sample size of 10. So now that we have that, we want to know what is the probability that at least half, okay? So we want to know in the second part, what is the probability that at least half of these people that we found in part 1 will pay their accounts before interest charges are incurred, okay? So the probability that the people that we found here on top, let's just call it pay bills before interest, and once again, divided by 2. So this is very simply 4 divided by 2. So I have the number of people that I'm looking for. So I want to know what is the probability that my x, so what I'm looking for, is greater or equals to 2, which is this number right here, which is what? It's the expected number of people that pay bills before interest cut in half, right? So I have my at least, I covered it right here. The half of what? Half of the number of people that are expected to pay their bills before interest is incurred, okay? So this right here, this is what I'm looking for. Erase this. And I know that because I want this like this, anytime that you have a probability of something like this where you have a greater than or x equals to something, whenever you have, what I'm trying to cue you into is whenever you have a sample size, like I said earlier, with 2 outcomes, right away you know that it's binomial, especially when they ask you for the probability of a given number, so x, being greater than or equal to a certain amount within a given sample size. That should always cue you into binomial. Anytime you see something like this, what is the probability that my x, so my number of people, is greater than 2? What is the probability that the number of hotel rooms is greater than 4 within 20 hotel rooms? Anytime you have the probability of a given element within a given sample size, that is always binomial, okay? So now I'm going to give you a little trick that always works for binomial. I covered it very quickly in the theory portion, but let's look at it in detail now. And this trick always works. It takes a second more in a problem, but I can guarantee you that if you do this, because most of you are visual, you will always get the right answer, okay? So what I like to do is I like to write out my sample size. So there's my sample size of 10. And then I like to literally just do an arrow for what I'm looking for. So I want to know what is the probability that at least, so this right here, at least half of the expected number of customers that pay their account balances before interest charges are incurred. I want to estimate the probability that it'll be greater than that, right? That at least half, so that greater than or equal to 2 people will pay their account balances before interest charges are incurred. So because I have greater than or equals to 2, now I hope that some of you noticed that I forgot something. In binomial, the 0 is super important. Why? Because there is the possibility that no people will pay their accounts after or before interest charges are incurred. Okay, so in binomial, the 0 is incredibly important. Please, 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 please do not forget it. Okay, so now what I'm looking for is x greater than or equals to 2. So this is what I'm looking for, right? I'm looking for the probability of x being greater than or equals to 2. Now, remember when I said the equal to was important? Why is it important? Because the fact that it's equal to means that the 2 is included. Okay, so notice how the 2 is within the box. So because the 2 is included, I'm going to put it within the box. So this is what I'm looking for. Now, I know that you're all very smart and that you can see that this implies in binomial doing the calculation for not 1, not 2, not 3, but 8 of these. 8 binomial formulas in an exam is incredibly tedious and long, and you won't have time for that. So let's be smart about this. What can we do also? You agree with me that we can do this right here. Okay, and this right here is what? Is the probability of x being less than or equal to 1, right? And this implies what? This implies calculating for just 1 and 2 binomial formulas. And then in order to get the complement, what do? We simply do 1 minus this. Okay, so let's go ahead and do it and you'll see what I mean. So let's start with the first one, which is the probability of x equals 0. Okay, and this is going to equal my n factorial. So 10 factorial divided by x factorial, so 0 factorial, multiplied by 10 minus, so n minus x, so 10 minus 0 factorial, and then this is going to be multiplied by the probability of what I'm looking for, so my p, my success, which here, because I want the number of customers that pay their accounts before interest, it's going to be 0.4. That's what I'm looking for, to the power of 0, so my x, times my q, which will be the complement, so 0.6 times 10 minus 0. Okay? Now, a few things I'd like to point out. The p will always represent your success. And what we mean by your success is what we're looking for. Okay? So the p will always be what you're looking for within a problem. So let's put that here. The p is always what you're looking for. And what are we looking for in this problem? We're talking about the people that pay their accounts before interest is incurred. So that would be my P. Whereas my Q will be what isn't referred to in the problem. So we'll just put the complement as opposed to putting what isn't referred to in the problem. It's also called the failure. Okay, so it'll be the complement. So here we know that we don't want the 0.6, which is after interest. So we don't want that. Okay, so that's how we know it's our Q. And then we simply solve for this. Now, for those of you that know some of the tricks of the binomial formula, you know that for the 0, this entire portion right here, I'll write it out for you guys. So you know that let's put it in yellow. So you know that for the 0, this entire portion right here will equals 1. So all you really need to punch into the calculator is this right here. This is just a little trick. If you're not comfortable with this, just punch it all out in the calculator. It's not a problem. But really just for the x equals 0, this entire portion will equals 1. So really all you need to do is compute the 0.6 to the power of 10, which is a total of 0.00604. Normally 4 decimals are fine, but since we would just have the 0060, I will just, out of precaution, just add one more. It'll actually be rounded up to 5. So let's just put the 5. And then the other one we need, so we cover the 0, then we need the 1, okay? So now we need the probability of x equals 1. And so we're going to rewrite the entire formula. 10 factorial. Now my x here is going to be 1 factorial. 10 minus 1 factorial. My p hasn't changed. 0.4. My x is now a 1. My q hasn't changed, 0.6, but now it's 10 minus 1. Okay? So this is going to give us a total of 0.0403. Okay? Now, once again, I'll show you the little trick for those of you that are comfortable. This portion right here for the 1 is going to equal 10, and then you simply multiply by the rest. Okay, so as you notice how the 0, this will be 1, then at the 1 it'll be 10, and then so on and so forth. But this is really just if you're comfortable. If not, like I said, punch it into the calculator entirely. Okay, so now I have my 0 and my 1. So now my third step, I'm not done, right? These are separate. I want the probability of it being less than or equal to 1. So I have to add them up, right? The probability of it being less than or equal to 1 is equal to the probability of x equals 0 plus the probability of x equals 1. So this is going to equal to 0.00605 plus the probability of 0.0403. So this is going to equal the probability of 0.04635. Now, are we done? No, we are not done. Very, very important. What did the question ask for? The question asked for the probability of x being greater than or equal to 2. Is that what we have here in part 3? No, this is the probability of x being less than or equal to 1. So what do we need to do to get what's in the red box right here? We're simply going to take, so in my part 4, to obtain greater than or equal to 2, I'm simply going to take this portion right here, which is the complement, right? You agree, I'm just going to switch colors here to show you. You agree that out of all of this little portion in yellow here is the complement of this entire portion in red. So what do you do when you have the complement? You simply do, to obtain the probability of x greater than or equal to 2, you do 1 minus the probability of x less than or equal to 1. So this is going to be 1 minus 0.04635. So this is going to give me a probability of 0.95365. And there you have it. Now, in the off chance that you are given the binomial table in an exam, side note that I really, really, really want you to remember, okay, I'm going to put it over here in a little box, okay? So this is a little side note that I hope you remember. So for the binomial table, if you are given a binomial table, always, always, always make sure that your probabilities are in this form, okay? So the probability of x something something, always make sure that it's in the less than or equal to form. Why? Because the tables are cumulative, which means that as you go down a column in the binomial table, you're adding things up, okay? For those of you that don't know what I'm talking about, go review the theory, the part 1 video of this section, and you'll see that I talk about this. In the table, in the binomial table, this right here, the red box, the greater than or equal to 2, is going to be very hard to find because you have to subtract going downwards. Whereas if you simply do the probability of x less than or equal to 1, you would simply go to the third row of the table. So 0, 1, the second row, I apologize. So the 0 and the 1, so less than or equal to 1, you would go to the row of x equals 1, and that would be your probability. and then you simply do 1 minus that probability to get greater than or equals to 2. Okay, so because the table is cumulative, always make sure that your probabilities are expressed in less than or equal to form in order to make it really easy for you to find a given probability within the table. And then if need be, you simply take the complement to get your final answer. Okay? Awesome. So stay tuned. We're going to do one more binomial problem, and then we're going to move on to chapter 5 problems. So now let's do a second binomial problem that's a little bit more complicated than the first one that we just did. A machine operator carries 15 batteries with him at all times. To run, the equipment, the machine, requires 10 working batteries. The batteries fail 15% of the time. What we want to know is, what is the probability that the operator does not contain enough good ones, so good batteries, to get the equipment running? So, what do we have here? Like I said, you guys know that I always like to break up the problem into something simple. So, the machine operator, he carries a sample of 15 batteries with him at all times, right? Now, we know that to run, the machine requires 10 batteries. So what does that mean? That means that he has 5 extra with him at all times, right? So what I like to do in this type of problem, I like to draw out these little circles. Now, it's a bit tedious, but these are all little tricks to get you thinking about things in the right way. Like I've always said, I know that most of you are very visual, so this trick really helps to understand this type of binomial problem. So let's just finish drawing all 15 batteries. So how many do we have here? 4, 8, 9, 10. And these are the 10 that are required for the machine to function. Now the other 5, I'm going to draw like this because they are just extras. Okay? So I have the 10 batteries that are required for the machine to function, and then I have the 5 extras. So let's just put it like this. These are the 5 extras. Sorry, some of them are a bit not as visible. Alrighty, so those are the 5 extras, and these are the 10 required. Let's put it like this. And these are the 10 required for the equipment to function, right? Now, what else do we know? Okay, so let's, as always, let's get into the habit of doing this. So we know he carries 15 batteries at all times. We got that. We know that to run the machine requires 10 batteries. We got that. The batteries will fail 15% of the time. So the probability of the batteries failing is equal to 0.15, right? What is the probability that the operator does not contain enough good batteries to get the equipment running? So right away, you should recognize, as you hopefully did in the last problem as well, that we have a binomial problem here. Okay, I obviously told you at the beginning of the question that it was going to be a binomial problem, but really I want you to learn to recognize it. How? We have a sample size. We have only one probability from which we can deduce the complement. And they want us to know within this given sample size, within the 15 total batteries, what is the probability that we can get the machine running so that we have enough good ones? So that means that we need a given number within a larger sample size, and we only have one type of probability, so one outcome from which we can deduce its complement. So we'll have 2 outcomes only. Binomial right away, guys. Okay, that should cue in to your head right away when you want a given number, the probability of a given number within a complete sample size, always binomial. Okay, so let's start by finding the complement. So the probability that the batteries will work is the complement. So 1 minus 0.15, which equals 0.85. Okay. Now, you're probably wondering why I drew the batteries up here at the top. Very simple. This type of problem also comes back in, let's say, hotel bookings or, seats at a concert or plane seats, like plane ticket seats. This is the type of problem that comes back in this form. Why? Because you'll always have a required number. It could be of rooms, of seats in a flight, like I said. It could be, in this case, the batteries. And then you'll always have some extras, okay? And the reason why I draw this out like this is to make it really easy for you to see how many batteries, so the probability that you would require for the machine to function or not to function, okay? So we want to know what is the probability. Oh, let's just actually take a second. Let's just cross this off. We're done with this as well, okay? Okay. So what is the probability that the operator does not contain enough good machines to get the equipment running, okay? Good batteries. So you agree with me that the probability of not containing enough good batteries means that you don't have your extras, right? So the extras are all failing. But is that it? No, we need for one more to fail, right? Because if all the extras fail, well, then the 10 required are working and we're fine. Our equipment's going to work. So in order for the equipment to not work, we need at the very least one more to not work, right? Within our 10 that are required. So you agree with me, and I did say at the very least for one not to work, right? It could be one or more. So what does this give us? Let's draw it out, write it out in probability form. So in order for the equipment not to work, you agree with me that the 5 extras have to fail, and at least one of the required fails, right? So what does this translate to in probability form? It's very simple. You already have the illustration up here, guys. Don't rack your brain over this, okay? Do you remember in the previous problem how we did our numbers? Okay, so let's just write them all out. So you already have it mapped out here. Now we have our numbers at the bottom. So what do we need? So this is 1, 2, 3, 4, 5, 6. So we need for 6, so these 6 right here, or more to fail for the equipment to not work, right? So you agree with me that this sentence right here translates into the probability of x being greater or equal to 6, right? Because you need for the 5 extras to fail and at least one of the required to fail. So that's greater than or equal to 1, okay? Because if 1 fails, the equipment won't work. If 2 fail, the equipment won't work, and so on and so forth. But it could be more than 1 is what we're trying to say. So the 5 extra absolutely have to fail, and then in the required, at the very least, 1 has to fail, okay? So that's a probability of x being greater than or equal to 6. So then this becomes, from this point, it becomes pretty standard like the other problem, okay? So I need to find the probability of x equals 6 if I rewrite this, if you're more comfortable, so once you've done the illustration, if you're more comfortable with what we did last time, don't be shy to just redraw it real quick. Okay, so we know that we need the probability of this right here. What did I forget, guys? Very important. Please don't forget this. In binomial, the 0 is super important, okay? When you're drawing it out like this, these are the actual physical batteries up here, so you don't need the 0. But down here, this way of doing it is really for the calculation purposes. So just be careful with the difference between the two, okay? This is just for you to see how many batteries out of the 15 would need to fail. But then when you're doing the calculation, you add the 0 because there is the possibility that no batteries at all have to fail, right? But what I'm trying to get you to understand is that here I put the 0 because I need to count out how many formulas I have to do, and the P of X equals 0 is one of them. Whereas here, if 0 batteries were failing, I would simply have 0 red X's, right? So just be careful with that. So now I know that this right here is the probability of what I'm looking for, which is X being greater or equals to 6. But this implies 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 binomial formulas. Whereas if I go backwards, this right here implies 1, 2, 3, 4, 5, 6. It's not much better, but it's a little bit better. So this is less than or equal to 5, right? Now, because we're all pro at doing these, I'm not going to write out all of the 5 formulas. What I would suggest you do instead is go grab the binomial table right now, and let's do it together with the binomial table, okay? So the first step to looking into the binomial table is to go to the right sample size, okay? So in this case, we're looking for n equals 15. So make sure that you're at the n equals 15 portion of the table. The second thing that we're going to look for is that we're at the right p. Okay, so go to the right p. And when I refer to p, I'm talking about p and q, so the two complements in the binomial. And here, what is our p? So go to the right p. We know that p is always what they're asking for in the question. Oops. Okay, so what are they asking us for in the question? They want the probability that the operator does not contain enough good batteries to get the equipment running, right? Now, do you remember how I was doing P of X equals greater or equal to 6? What does that imply? That implies that I'm using the probability of failures as my P, right? Because I'm saying that 6 or more batteries have to fail for the equipment to not work, right? So what I'm using here, what the question is asking for, I use the batteries fail probability, right? So I use the probability of batteries failing. So my P in this case is going to equal 0.15. So I would go to P equals 0.15. Now, I'll put a little asterisk here because I'm going to go over something afterwards for this particular problem, okay? So I'll cover that in just a second. Now, my third thing is I have to make sure that what I'm looking for in the table is structured in the less than or equal to form, okay? Make sure that your X is structured this way. to make it easier to look in the binomial table because the binomial table is cumulative. Okay, so what do I have here? I'm looking for the probability of 6 or more batteries failing in order for the equipment to not work, which is equal to 1 minus the complement that we found right here. So P of X less than or equal to 5. Okay, so then what do I have in the table? You went to N15, P of 0.15, and then on the left-hand side, you'll see the x's. X equals 0, 1, 2, 3, 4, 5. So then you know that the number that you're going to find right here at x equals 5 is everything included up to 5, right? So it contains the 0, the 1, the 2, the 3, the 4, the 5. Why? Because binomial tables are cumulative. Okay? Binomial tables are cumulative. So you remember from the theory, the cumulative means that at this line right here, this is equal to the probability of x being less than or equal to 5 because it contains everything leading up to the 5, including the 5, right? So that's why I always suggest you structure your binomial problems this way to make it really easy to look at the table. Because if you were in the greater or equal to 6, you would have to go down and subtract like backwards, for lack of a better expression, which is just complicated for no reason when you can just do 1 minus this answer right here afterwards, right? So then we grab this number right here, which is equal to, let's put it in a different color. Okay, so this is 0.9832. All right. All right, and then are we done? No, we're not. Very important. This isn't the final answer. Okay, this is the complement of what we want. So then in the fourth step, please, please, please do not forget this step. We have to do 1 minus P of X less than or equal to 5. So if you're looking in the binomial table, unless they were obviously asking for this portion, don't forget this extra step where you have to take the complement. So it's 1 minus 0.9832, which is equal to our answer, which is 0.168. Okay, so this is the answer to the problem. Now, do you remember when we were solving the problem? I went up to here and I hadn't gone over what the P was yet. We only covered the P right here when we said go to the right P when looking in the table, right? Why did I wait all the way until here to do this? Because this problem can technically be solved 2 ways depending on what you use as the P, okay? What do I mean by that? I want you to pay close attention here, okay? I said that what we're trying to look for is we simply want to know at what point will the equipment stop working, right? What we mean by that is in order for the equipment to not work, 1 or 2 things has to happen. If we're using the probability of the batteries failing, then 6 or more batteries have to fail for the equipment to not work, right? But what if I'm using the probability of the batteries working? What does that mean? So in the same way that if I'm using the probability of the batteries failing, we would need, so let's put it right here. So for the failure, we would need for 6 or more to fail, for the equipment not to work, right? Which is what we have here. But we could also say that if in the PQ I'm using the probability of the batteries working, now notice, watch this. Okay, this is how it's a perfect complement. Let's put it in orange. This is if I'm using the probability of the batteries working, okay? Because If 6 or more have to fail for the equipment to not work, then out of 15, what does that mean? That means that 9 or less have to work in order for the equipment to fail, right? Look up here, okay? These are our physical batteries. Remember, these are like the little drawings of our batteries. Now look at how it's a perfect complement. If 1, 2, 3, 4, 5, 6 or more fail for the equipment to not work, where do we draw the line? We draw the line right here. So that means that 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 or less have to work in order for the equipment to fail, right? Now, I understand that in terms of the concept, like psychologically, it's easier to say because we're asking for the equipment to not work, to also think of the batteries not working. The two would go hand in hand, as opposed to thinking of, oh, how many batteries have to work for the equipment to not work. It's a little bit more confusing. So I do see that the P of X greater or equal to 6 is easier to frame the problem. I agree. But I just want you to realize how perfect complements they are. So in the same way that when we look at these two right here, the probability of the batteries failing and the probability of the batteries working, these are perfect complements, right? 0.15 and 0.85. Well, the way that you structure how you solve the problem is also a perfect complement. Depending on what P and what Q you choose, because this question is a bit more of an open-ended question, right? They're simply asking for what is the probability for the equipment to not work. Depending on what you pick as your P and your Q, you can structure your problem differently, okay? So there are two ways to solve this. You can either choose, if you pick the probability of the batteries failing, to do the P of X greater or equal to 6, which means that if 6 or more batteries fail, the equipment will stop working. Or if you choose as your P the 0.85, which is the probability of the batteries working, then 9 or less batteries have to work for the equipment to stop working, okay? So look at it this way. The 6 or more for the equipment to fail, and then if you count these out, there's the 9 in here. Now, I don't want you to get confused, okay? I think it's easier to look at the physical batteries. You have 6 or more have to work for the equipment. 6 or more have to fail, I apologize, for the equipment to stop working. Or 1, 2, 3, 4, 5, 6, 7, 8, 9 or less have to work for the equipment to stop working, okay? The idea here with the binomial formula numbers is that it's the same thing that we're looking for, right? Which is this right here. It's the same thing. So whether we're looking at 6 or more failing or 9 or less working, we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 10, right? Because the 9 or less implies the 0 and the 6 or more includes the 6, okay? But I just want you to see how this right here and this right here are perfect complements, okay? Which relates to the physical batteries here, 6 or more, where we drew our two lines, or 9 or less, okay? Perfect complements in the same way that the P and the Q would be perfect complements. So what would this imply? Going back to my little asterisk right here, what I'm trying to highlight is, like I said, as much as the P and the Q, depending on which one you pick, are perfect complements, in the same way, the way that you structure the problem, so what you assign the P and the Q to, could mean that you could solve the problem in two perfect complementary ways. So if I go back to my asterisk right here, the first time we did it with the probability of the batteries failing, so let's just erase this and do it now with the probability of the batteries working. So that would be my 0.85. So in the table, I'm still going to look at my sample size N15, but now I'm going to go to P of 85. But now this is going to change a bit, right? Part 4 is going to change a bit. I'm no longer looking for this right here. I'm now going to be looking for this right here for the probability of the batteries working. So that's P of X less than or equal to 9. So 9 or less have to work in order for the equipment to not work. Because if 9 or less work, that means I don't have enough. I need 10 for the equipment to work, right? So let's just erase this right here. So then you would go into the binomial table at N15, scroll to the P that you're looking for is now 0.85 as opposed to 0.15. We're looking for the probability of the batteries working, but our X has now changed, okay? So 9 or less batteries have to work. So then in our rows, we're gonna go all the way down to, so let's just erase these. I wanna show you. So we're gonna have our 0, and then we're gonna go all the way down to our 9. And then at our 9, we're going to find the answer directly because we don't need to do 1 minus anything. So it's just going to be the answer because we took the probability of the batteries working. Okay? So N15, that hasn't changed. We went to P of 0.85 this time because we're looking for the probability of the batteries working. And then our X changed as well. Remember, perfect complements, P of X less than or equal to 9, or P of X greater or equals to 6. And what I mean by perfect complements is the 9 plus 6 will equal the total 15 batteries, right? So it's perfect complements in terms of what you're taking. Either 6 or more will fail, or 9 or less will work, right? So those are perfect complements in the total 15 sample size. And then if you scroll down to the 9, you'll get 0.0168, which is the same answer, okay? So what I'm really trying to show you here is that because this is a bit more of an open-ended question, I repeat, all we want to know is what would be the probability of the equipment, like the minute, what would be the probability the minute the equipment doesn't function, right? The minute you don't contain enough good batteries for the equipment to work. So all we want to know is really the probability of the equipment not working. Right? Now that could be framed 2 different ways, depending on what you choose as your P and your Q. If you choose the failure, 6 or more have to fail. Okay, so look up here at the physical batteries, 6 or more have to fail. Okay, and that would imply that if you choose the probability of the batteries working, that 9 or less have to work. Okay, so perfect complements in the total numbers in the sample size, which makes perfect sense, right? And perfect complements in the probabilities that you choose. Okay, so just keep that in mind. Like I said, I understand that it's easier to frame in terms of the failure because you want the equipment failing, batteries failing. It just goes hand in hand. But know that you can do it both ways depending on what you're most comfortable with. Okay, just make sure that you assign the right P and the right Q to the right probability that you're looking for. So the right X amount of, in this case, batteries that you're looking for. Okay, so now I showed you this is a bit of a tougher binomial problem. So now let's move on to the final set of questions, which are the continuous probability questions. All right, so now let's move on to a discrete probability problem, which I really like because it covers a little bit of what you see in typical probabilities, and it covers some of the discrete probability aspects, okay? So let's dive right in. The transit system in Euralia has first, second, and third class seats, all with regular fares and reduced fares. Reduced fares are for seniors and children and are 15% of the regular fare. 90% of riders in first class pay the regular fare of $4 and the others pay the reduced fare. 70% of riders in second class pay the regular fare of $2 and the others pay the reduced fare. And 80% of the riders in third class pay the regular fare of 50 cents. And then they go on to tell us that 20% and 30% of the riders are in first class and second class, respectively. Okay? So I'm going to solve this both ways. I'm going to use the tree first, and then I'll quickly show you how to do it with the table, just depending on how you're more comfortable. Okay? So this is what I like about this problem. We're first going to start by mapping out the tree and the table, and then from then we'll be able to solve for all the different probability items that we need. Okay? So before we even get started with A, B, C, D, E, let's just map everything out. Righty? So remember from a theory, the first level should contain your main probability items, and then the second level will contain the conditional, right? So what would you say would be the first item? I think you would all agree with me that the first item should be first, second, and third class, because in the level 2, in the second part, the second branches of the tree, we're going to have, given that you belong to first, second, or third class, you pay a specific fare, right? Reduced or regular. So my first branch should be first, second, and third class. Okay, so let's just put first, second, and third class. And then, so this all stems from the same dot. And then given that you're first class, you'll either pay regular or reduced fare. Okay. So regular or reduced. Given that you're in second class, you'll either pay regular or reduced fare. And given that you're in third class, you'll either pay regular or reduced fare. So I'll put the little legend up here so nobody gets confused. So R is for regular. RF is for reduced fare. Okay, that way we won't get confused. And then FST, first, second, and third class. Okay, so what do we have here? From the second part of the problem here, we know that 20% and 30% of the riders are in first and second class. Okay, so let's just cross this off. So 20% of the riders are in first class. So here we have 0.2 for first class. And then 30% of the riders are in 30% are in second class, okay? Because they say respectively, so that means it's one after the other. So here we have 30. And because they stem from the same knot, these three branches, first, second, and third class, have to equal 1. So this here for third class is going to be 0.5. Okay? So now that we have that, let's move on to the reduced and regular fare. So the second level of my tree. At the top here, they tell me, okay, this is, we don't need this really. This is just a little bit of blah, blah, blah. Reduced fares are for whom, that's fine. This we might need a little bit later, the 50% of the regular fare. But for now, I want to know what's the probability between the regular and the reduced fares. So I know that 90% of the riders in first class pay the regular fare of $4. Okay, so this here is a probability of, I won't put it here. So this here is a probability of 0.9. And I know that because it stems from the same knot, the reduced fare will be 10% of people. Okay, so I have this done. 90% of the riders in first class pay regular fare, and the others, the 10% remaining, pay reduced fare. 70% of the riders in second class pay regular fare. So this right here, I know is going to be 0.7, and the remaining pay reduced, so that's 0.3. And finally, 80% of the riders in third class pay regular fare. Okay, so that's going to be 0.8 right here, and the remaining pay reduced fare, so that's 0.2, right? So remember from the theory, the first part is your main probability item, and the second part is your conditional. So given that you belong to first class, 90% of you also belong to regular fare, okay? And then the final item is the and, remember? So let's just move these a bit. Okay, so this here is going to be first class and regular fare. This is going to be first class and reduced fare. Second class and regular fare. Second class and reduced fare. Third class and regular fare. And third class and reduced fare, right? So they want to know in part A, what proportion of riders pays regular fare, okay? Now, the only way that we can solve for that is if we isolate right here for the regular fare, right? We need to determine the probability of regular fare, which can only be done when you add, I'll draw it right here for you to see. So you need to add the portion of regular fare that is first class, the portion of regular fare that is second class, and the portion of regular fare that is third class, right? In order to get all regular fare. Okay, you have to add up all its subsector elements. So that's what we're doing right here. So we need to determine these first. So this is going to equal to 0.2 times 0.9, so 0.18. This is going to equal to 0.3 times 0.7, so 0.21. And this is going to equal to 0.2 times 0.8, so 0.4. Alrighty, so now we can add up, if we take these three items and add them all up. So I'm just going to put this in a different color so you see. So let's add this one right here, and this one right here, and we'll add them all up. Okay, and we'll obtain a total of 0.79, and that's the probability of regular fare, which is what proportion of riders pay regular fare. So the proportion of riders that pay regular fare, we just found it. We added up first class and regular fare, second class and regular fare, third class and regular fare, and what do they all have in common? Regular fare. So that's 79% of riders pay regular fare. Okay. Now, part B. If, remember those keywords, guys, okay? If a rider is selected at random, okay, so this here, apologize, so this is part A. Part B. If a rider is selected at random and found to have paid regular fare, what is the probability that he is a first class fare rider? Okay, so I repeat, if a rider is selected at random and found to have paid regular fare, so if regular fare, what is the probability that this person belongs to first class? So we know that this is the probability of first class and regular fare. And we're going to divide this by the condition, which is given that you belong to regular fare. So R right here. And then we found the bottom from part A, so 0.79. And the top we have right here at 0.18. And so this is equal to 0.2278. Okay, so here's part B, 0.2278. Now, part C. What is the mean amount of money paid per rider? Okay, we want to know what is the mean amount of money paid per rider. Now, in order to solve for part C, there's one thing that we're missing. So we know that the level 3 of our tree, so the final branches of our trees, all the ends are the final outcomes, right? So you have first, second, third class. Then you have for each one regular and reduced fare. And at the very end, you have all the different categories that you'll have. So you have the people that belong to first class and regular fare, second class and regular fare, third class and regular fare. And you'll also have the people that belong to first class and reduced fare, second class and reduced fare, third class and reduced fare. And all of that makes up the entire population, all people that you're looking for, right? Those are all the subcategories, all 6. So before we move on, we need to find the ends for the reduced fare, okay? So this here would be first class and reduced fare, so it's 0.2 times 0.1, so this is 0.02. Here, second class and reduced fare is 0.3 times 0.3, so this is 0.09. And third class and reduced fare is 0.5 times 0.2, so this is 0.1, okay? And then we're going to add all these up. Once again, I'll do these in yellow. So we're going to isolate for all of the reduced fares right here. Okay, so I'm going to add this, this, and this. And so the probability of reduced fare, because that's what they all have in common, it's going to be 0.21. And remember when I told you that if you did this right, if you add these two up, because it contains all the elements, all the events of this population, it'll add up to 1. Okay, so we got it here, so we know that we're doing it right. And now they want to know what is the mean amount of money paid per rider. Okay, so what do we have to add to this? We know that the people that belong to first class and regular fare, they pay $4, right? So let's add these up in white. So these people pay $4. The people that belong to second class and regular fare, which is right here, they will pay $2. And finally, the people that belong to third class and regular fare, they will pay 50 cents, right? 50 cents. And remember from the beginning when I told you that we couldn't exclude, let's do it like this little portion right here. So the reduced fare are for these people, and the reduced fare is 50% of the regular fare, okay? So like I said, remember, I always tell you, don't rack your brain over this stuff. It should be straightforward. If you don't know what the reduced fare is and you're wondering why, go back and read the question. Maybe you missed something. So we know that the reduced fare for first class is 50% of $4, so it would be 2. The reduced fare for second class is 50% of $2, so it would be 1. And the reduced fare for third class is 50% of 50 cents, so it would be 25 cents. Okay. And now the reason why I love this question is because up until now, we've pretty much just done a regular type of probability problem solving, right? We did our tree. We found all the different types of probabilities. Question B, it was a simple conditional that we had to solve for. And now in question C, when they're asking us what is the mean amount of money paid per rider, what do we have to do? Well, I'll show you right here. So question C, let's write it a little differently and you'll understand. Okay, let's pretend that we have our x right here and then our p of x. And you recognize this as the discrete probability chapter when you have your different outcomes and then your different probabilities. So my different outcomes are going to be the different fares that I'm going to be paying. Okay, so we're going to pay either a fare of $4, $2, $1, 50 cents, and 25 cents, right? So this is first class regular fare, first class reduced fare, second class regular fare, second class reduced fare, third class regular fare, and third class reduced fare, right? So to each one of these, you're going to assign its given probability. So this is 0.18, 0.02, 0.21, 0.09, 0.4, and 0.01. And then this is fairly straightforward. You guys remember that in the discrete, to solve for the expected number, we simply take the sum of each outcome times its given probability, and we add them all up. So we're going to do 4 times 0.18, 2 times 0.02, 2 times 0.21, 1 times 0.09, 0.5 times 0.4, 0.25 times 0.01. And this is going to give us a total of $1.495. Okay, so the average amount paid per rider is $1.495. Now remember when I told you we're done with this part of the question, so let's just cross this off right here. But we still have a second part. They want to know what is the mean amount paid per regular fare rider. So which ones are the regular fair riders? We have this piece right here, this piece right here, and this piece right here, right? So now I want you to pay close attention here for part D. I want the expected dollar amount per regular fair rider, and this is going to equal to 4 times 0.18 plus 2 times 0.21 plus 0.5 times 0.4. But what am I missing? And this is crucial. A lot of you will forget this in a problem like this. You have to divide by 0.79. Because essentially, what is a mean? If we take it back to the basics, a mean is usually the sum of the x's divided by the given sample size, right? So if we're 10 people in a room, we would do, let's say, we add up everyone's age, and then we divide by the 10 people to determine the average age, right? Now, the reason why in part C we don't divide by anything is because what are we doing? We want the mean amount paid for all riders. And you agreed with me, if we look over here, that all riders make up the total population of riders, if you will. And so the probability will equals 1. So what am I doing? I'm doing the probability of everything divided by 1, which is the total population, right? So you can't really see it, but technically here, we're taking the sum and we're dividing by 1 because it's the probability of all, right? I'm taking the sum of all the outcomes times all their given probabilities, and I'm dividing by the total probability of this population, if you will, which is 1, right? Whereas in part D, I only want the mean amount paid per regular fair riders. So I take the probability of all the regular fares and multiply them by their given outcomes. But then because it's only for the subset of regular fare, I have to divide by 0.79, okay? Because that is right here. The subset of regular fare is only 0.79. So it's like if I'm doing the average age, for example, of only part of the population. So my sample size has to be reflective of the part that I'm taking the average of, right? So here it's the total. So it's a probability of 1. So 100% it's the total. Whereas here, it's only the subset of regular fare, which is a probability of 0.79. And so this is equal to 1.696, okay? Oh, sorry, that wasn't part D though, I apologize. This is still part C, just the second part of part C, okay? So now we've covered this as well. So now that we know, we're done with part C, okay? So just be careful, I apologize. It's C here and not D. It's the second part of C. Okay, so just be very, very careful. Can't stress this enough. Normally, you don't see this here because we always divide. We want the mean amount of something and it's usually on the total, so we divide by 1 so you don't see it. But when you want a subset of the total, remember to divide by the subset's probability, okay? So now I'm going to erase some of this just because I'm running out of room a bit, and then we're going to do D and E. Alrighty, so now let's do part D. Okay, so now in part D, they want to know, a transit authority spot check is made by selecting 8 riders at random. What is the probability that at least 2 of them are reduced fare riders? So remember when I told you that the minute you see a given number of riders selected within a subset, binomial, that should have lit in your head the minute you read that, okay? So we have a sample size of 8 selected at random, and we want to know the probability that at least 2 are what? The P that I'm looking for is reduced fare, right? So right here, reduced fare riders. So because I have one given outcome from which I can deduce the complement, which we know already for the regular fare to be 0.79. And because I want a certain number, so at least 2 out of a given total, 8, I know right away that this is binomial. So let's do our little binomial formula check. Okay. So at least 2. This involves a lot of calculation. So we're going to be smart and compute just for the complement. So I'm going to compute for the probability of P of X less than or equals to 1. And so that implies computing for P of X equals 0, to which I'm going to add P of X equals 1, right? So for P of X equals 0, I know that the first portion of the entire portion of the binomial formula will equals 1, except for the q to the power of n minus x. So this is going to be 0.79 to the power of 8. And that's equal to 0.1517. Now, for those of you that don't know what I mean by that, I suggest to go watch the video where I solve a binomial problem for the first time, and you'll understand right away what I'm saying. And for the P of X equals 1, I know that the first portion of the equation is equal 8. And I'm simply going to take 8 and I'm going to multiply it by 0.21 and then multiply it by 0.79 to the power of 7. And this is going to equal 0.3226. So once again, for those of you that are a bit confused, I suggest you go watch that portion of the binomial problem. And so I'm going to add these two up. Okay, so let's just add them up right here. And this is going to equal a total of 0.5257. But am I done? No, because what I want is this right here, right? P of X greater than or equals to 2. So please don't forget to do 1 minus P of X less than or equals to 1. It'd be silly to lose points because you forgot that final step. So it's 1 minus 0.5257, which is equal to 0.4743. Alrighty. So that's the first part of that question. Because remember, don't forget to do this here. We just solved for this part of the question. And the second part of the question says, what is the expected number of reduced fare riders amongst the 8? So we're going to continue in the same line with binomial type problems. And we know that to get an expected number, so here we want the expected number of reduced fare riders among the 8. We're simply going to take our n and multiply it by our p that we obtained. And so what is the expected number of reduced fare riders amongst the 8? That's going to be 8 times the probability of being reduced fare, which is 8.21. That's equals to 1.68. Okay, so my p that they want is being reduced fare, which is 0.21. Okay, we know from right here also. So that was that. So now we solve for this portion right here. We're done with this. And what is the standard deviation? We know that the standard deviation is simply n times b times q for the n that we're solving for, not that we obtained, but for the n that we're solving for, is what I meant to say. So we're going to do 8 times 0.21 times 0.79. The square root, please don't forget the square root, and the standard deviation is equal to 1.15. Okay, you could have just also done the square root of 1.68 times 0.79. That would have worked as well. Okay, so now we've solved for everything in part D, and we can move on to part E. Okay, so finally, part E. If there are 75,000 riders randomly selected on a given day, Okay, so if n is equal to 75,000, what is an estimate for the total amount paid in fares on that day? Now, there are two ways to do this, okay? One, you know that the expected amount paid per rider is equal to 1.495, right? So for those of you that are a little bit more comfortable with the theory, you know that the expected total fare would equal the average amount paid multiplied by the total riders within a given day, right? So if on average riders pay $1.495 and there's a total of 75,000 riders, then that's going to equal a total of $112,125, right? What you could have also done, for those of you that are a little bit less comfortable with the shortcuts, you could have simply taken, you know that the probability for each of the subsectors is, so you could have taken n times p, right? Remember the expected number of something. Let's say here I want reduced and first class. You could have simply done n times p. You know that the probability of reduced and first class is 0.18, and there are 75,000 riders total. So that would have given you 13,500 riders here, and so on and so forth. You could have taken the number of riders in each subsector and multiplied by their fare. It would have given you the same thing. But like I said, if you're comfortable with the shortcuts in the theory, you know that if on average this amount here is paid per rider and there are this many riders total, then this is the total amount that's going to be paid on average, right? As opposed to taking the 75,000 and determining how many riders are in each subcategory and then multiplying by each of the sub fares. It's a bit longer, okay? So now that we've solved for that right here, which is our E, I want to show you real quick how this tree would look like in a table for those of you that are more comfortable with the table, okay? And then you can just re-walk through the problem and solve everything for the table on your own. All right, so we know that for the table, we would have first, second, and third class. We have our totals at the margins. And then here we would have regular fare and reduced fare. And once again, our totals at the margins, right? So remember in the theory what I told you, the table is great for showing you the intersections, so the ands, whereas the tree is good for showing you everything. Simply you have to calculate the ands at the very end, right? So first class and reduced, we would need to compute it, okay? So this is why for this particular problem, I like the tree, because everything that's given to you in the problem is this portion right here of the tree, and you have to compute this. So by putting these down, you can see easier what it is that you need to compute for. Whereas the table in this particular example, you have to know where you have to put things in the totals, which can be a bit more confusing. It's really entirely up to you though. So depending on what you're most comfortable with. So what would we need to isolate for in the problem in order to be able to solve for the table? We need the totals, right? So what do we know here? We know that 20% of riders are in first class. We know that 30% are in second class. And then by default, because this has to equal 1, 50% are in third class. What else can we solve for here? Really nothing, which is why in this particular example, I like the tree. Everything else has to be deduced from the conditionals, right? So we would have, right here, we know that 90% of riders in first class pay regular fare. So given that you're in first class, those that pay regular fare is 0.9, right? So if I multiply this 0.9 times 0.2, I'm going to obtain right here, which is my end, which is 0.18. So notice how it's a bit more complicated in this particular example for the table, right? So this would give me 0.02 because it's simply 0.2 times 0.18. Then I know that 70% of the riders in second class pay regular fare. So given that you belong to second class, those that pay regular fare is 0.7. And I need to multiply this by the condition to isolate for regular and second class. So my condition is 0.3. So this would give me 0.7 times 0.3, which is 0.21. And then 0.3 minus 0.21, here is 0.09. And then I would do it for the last one. So given that you belong to third class, how many belong to regular fare? And that is 0.8. So to isolate for the and, the intersection right here, I need to multiply by the condition, which is my total right here. So 0.5 times 0.8, that's 0.4. 0.5 minus 0.4, 0.1. And then you can simply add these up. The totals at the margins, and this should always add up to 1. The margins should always add up to 1 right here, right? So notice how it's a bit more complicated for the table for this particular example, because you have to know that the conditionals need to be multiplied by the totals in order to isolate for the intersections. And remember, it has to be multiplied by the total of the condition, okay? Because if not, you'd be solving for something different, right? Remember, the condition is not interchangeable. So f given r is not the same thing as r given f, because the condition is going to be in the denominator, right? Alrighty, so now we're going to move on to 2 continuous probability problems, and that will conclude our part 2 review for the midterm problems. So let's move on to the final portion of the review part 2 for the Comm 215 midterm, which is the continuous probability questions. So let's dive right in. The length of a metal rod produced by a manufacturing process is normally distributed with a mean of 140 millimeters and a standard deviation of 0.2 millimeters. So right away, there are a few cues to let us know that we're in a continuous probability question. So the first thing we see right here is they talk about normally distributed. Right away, that should cue you into a continuous probability problem, okay? So normally distributed, we're going to have our bell-shaped distribution. And then they say that the mean is equal to 140 millimeters, and the standard deviation is going to equal 0.2 millimeters, okay? So then we can go ahead and solve. So we literally covered everything in our question. You know how I like to break it down into a very simple form. So we covered the mean, and we covered the standard deviation, and we know it's normally distributed, so we can use the bell-shaped curve. Now in part A, they want us to compute the probability that a randomly selected rod is longer than 140.5 millimeters, okay? So in part A, essentially what they want is the probability that a rod is longer than 140.5 millimeters, okay? So let's say that we have 140.5 is here. What do they want? Essentially, they want the probability that a rod is longer than this. So they want this portion of the bell-shaped curve, right? So how do we determine this? We first need our z-score, and then with our z-score, we're going to be able to go look at the z-table for the probability, okay? So first step, we need our z-score. So the z-score is going to be my x, 140.5, minus my mean, 140, divided by the standard deviation, which is 0.2. This is going to give us a z-score of 2.5. So in the z-table, on the vertical, we're going to go look for 2.5. And on the horizontal, because it's the second decimal, we're going to look for the 0, because here it's essentially a 0. And we're going to look for the cross between these two. So this right here is the number that we want. And this is represented by a total of 0.4938. So 0.4938 is what we're looking for. But then are we done? No, we're not done. Why? Because what I'm trying to isolate for is this tail end portion of the curve. So what does that mean? Because we know that the bell-shaped curve is evenly distributed into 0.5 and 0.5, okay, adding up to a probability of 1. What we're going to do in the third portion is, in order to isolate for the red tail right here, we're going to take 0.5 minus the probability that we found, which is right here. So this right here is 0.4938, but we're trying to isolate for the tail. And so this is going to equal 0.0062. So that right there is the answer. That's the probability that a randomly selected rod is longer than 140.5 millimeters. Okay? Okay, so let's move on to part B. Alrighty, so let's just redraw our bell-shaped curve. We know that our mean is at 140 millimeters, and our standard deviation is at 0.2. And now we want to know the probability that a randomly selected rod lies between 140.2 and 140.5. Okay, so now pay close attention. This part right here we found in part A, and we know to be 0.4938. So now what we need is to isolate for this part right here, right? So we're going to repeat the same process that we did in part A. So we're going to find our Z first. So it's going to be 140.2 minus 140 divided by the standard deviation of 0.2. So this is going to equal a z-score of 1. And then we're going to go in the Z table. So we're going to look for 1 on the vertical and 0.00 on the horizontal. And we're going to isolate for the cross between the two, which is this right here, which is going to equal a z-score of 0.3413. So that's going to be this right here is going to be a z-score of 0.3413. And because we want to know simply this portion right here, what are we going to do? So we want to know the probability of our x lying between 140.2 and 140.5. We're simply going to do the larger piece, so 0.4938, and we're going to subtract the smaller piece, so 0.3413, and this is going to equal a probability of 0.1525. And there you go. That is part B, which is the blue section right here. So now let's move on to part C. Okay. So in part C, they want to know So in part C, they want to know A rod is considered defective if it is less than 139.8 millimeters or if it is longer than 140.2 millimeters. Okay, so a rod is considered defective if it falls below 139.8 millimeters or if it goes above 140.2 millimeters, right? Compute the probability that a randomly selected rod will be defective, okay? So we agree that a probability of a rod being defective is this and this right here, okay? It's both because it's either defective if it's above 140.2 or it's defective if it's below 139.8, okay? So from part B, we already know that this section right here is going to equal 0.3413. And if you notice, the difference between these two and these two is 0.2, right? Except this is negative 0.2, which is going to give us a z-score of negative 1. And this is simply positive 0.2, which gave us a z-score of 1. But because the z-table is in absolute value, the probability will be the same. So this here will also give us a probability of 0.3413. But what I want is the two tails, right? So I want the tails in red. So what will we do? Let's solve for this one right here. And we know that this one right here is going to be 0.5 minus 0.3413, which is equal to 0.1587. And here it's going to be the same thing. It's going to be 0.5 minus 0.3413, which is going to equal 0.1587. And so the probability of a rod being defective is going to be this and this. So we're going to add them up. So the probability of a rod being defective is going to equals 0.1587 plus 0.1587, and this is going to equal 0.3174. Okay, so this is the probability of a rod being defective. So this is question C. And then finally in part D, so this is C right here. Finally in part D, they want to know if a sample of 15 rods is selected, compute the probability that there will be. So in part 1, they want to know the probability that there will be no defective rods. And in part 2, we'll do it over here. They want to know the probability that there will be exactly 5 defective rods, right? So right away, I hope the light went off in your head. This is binomial. We want a given number within a full sample size. So this is a binomial problem. So P of X equals 0. And they want the probability that there will be no defective rods. So remember the problem that was open-ended that we could solve both ways? Depending on what you pick as your P or your Q, you can solve this problem both ways. So I'm going to pick as my P the probability of a rod being defective, which I just computed for. So 0.3174. So if I want there to be no defective rods, and I picked P as my success of the rods being defective, then P of X will equal 0, right? If I had picked the P to be the rods being non-defective, then all 10, P of X would have had to equal 10, right? So I'm going to solve for P of X equals 0 using the probability of defectives. So this is going to equal my 15 factorial divided by 0 factorial, 15 minus 0 factorial times 0.3174 to the power of 0 times the complement, 0.6826 to the power of 15 minus 0. And if you remember from what I taught you in the first ones that we were solving, this right here for the x equals 0 is going to equal 1. So this is all I need to put into the calculator. And this is going to equal 0.0033. Okay, so that's for no defective rods using the probability of the rods being defective as my P. So now if exactly 5 rods are defective, using the probability of the rods being defective as my P, it's going to equals P of x equals 5. If I was to use no rods being defective, I would have had to use P of x equals 10, right? And here, I apologize, I believe earlier I said P of x equals 10. It would have been all of them, so it would have been P of x equals 15, not 10. Okay, so what I mean by here in part 1, because I picked P as the rods being defective, for there to be no defective rods, it has to be P of x equals 0, because I used the probability of rods being defective. If I had used the probability of rods being not defective, for there to be no defective rods, it would have had to have been P of x equals 15. That's what I meant earlier, I apologize. So here, because I want 15 to be exactly defective using the probability of the rods being defective, once again, is my P. My P is equal to P of x equals 5. Whereas if I had used the probability of rods being non-defective as my P, I would have had to have been 10 here, okay? So then we simply solve for this using the same binomial formula. So we'll plug in accordingly. And so this is going to give us 15 factorial divided by 5 factorial times 10 factorial multiplied by 0.3174 to the power of 5 multiplied by 0.6826 to the power of 10. And this is going to give us a total of 0.2110. Okay, so that's it for the second one. So now let's move on to one final question, and that'll be all for the review of part 2. So in this final question, they want to know the length of time it takes Revenue Canada to send refunds to taxpayers after the return is received is normally distributed with a mean of 12 weeks and a standard deviation of 3 weeks. So let's go ahead and draw our bell-shaped curve. All right, so we know that the mean is 12 weeks and the standard deviation is 3 weeks. And how do we know this? Well, we have this right here, which we covered, and then we know it's normally distributed, so we can use the bell-shaped curve, right? Now, in part A, they want to know what proportion of taxpayers should get sent a refund within 6 weeks. Okay, so within 6 weeks, that would be this portion right here. So we want to know what percentage of people should get their tax refund in 6 weeks or less, right? Within 6 weeks, that means that it'll take no more than 6 weeks. So let's start by finding our Z. So in part A, we're first going to look for Z. So that's my x of 6 minus my mean of 12 divided by my standard deviation of 3. This gives us a z-score of -2. Now be very careful, guys. It's -2. It doesn't make a difference for the z-table because it is an absolute value. But if you are asked to find a z value as an answer and you put 2 as opposed to -2, then it is wrong. Okay, so just be very careful. So now in the z-table, we are going to find the cross between 2.0, and there's no decimals, there's 0, 0 here, which is this number right here, and this is z of 0.4772. And are we done? No. Why? Because we're trying to isolate for the tail. So we know that this right here is 0.4772, but this is what I want. So I need to do 0.5 minus 0.4772. And this is going to equal the probability of my x being less than or equal to 6, which is equal to total of 0.0228. Okay, so that's the probability that taxpayers will receive their refund within 6 weeks. So let's move on to part B. What proportion of refunds will be sent more than 15 weeks after the tax returns have been filed? Okay, so I'm not going to erase the other part because we're moving to the right-hand side of the curve now. So we want to know what proportion of refunds will be sent more than 15 weeks after the returns have been filed. So that's this tail right here. So once again, let's compute our z. So this is going to equal to my x15 minus my mean 12 divided by the standard deviation, which gives us a z-score of 1. Okay, so in the z table, we're going to go look for the cross between 1.0 and 0.00, and that's this right here at, we've already found this one before, 0.3413. That's that right there. Are we done? No. Very important. We're trying to isolate for the tail. So the x being greater than or equals to 15 weeks, and that's equal to 0.5 minus 0.3413, which is equal to 0.1587. And so that's the probability the taxpayers will receive their refunds within more than 15 weeks. Okay, so after 15 weeks have passed. Now, one thing I want to point out, for the continuous probability problems using the bell-shaped distribution, the equal sign doesn't really matter because falling exactly on 15 is actually a probability of 0. If you fall exactly on this line right here, that's a probability of 0. So whether you put greater than 15 or greater than or equal to 15, it really doesn't matter, okay? Since you're isolating for an area and not so much one specific point on the curve, okay? So now let's solve for part C. Okay, now this is something I want you to pay attention to because C is worded a little bit differently. They want to know how long will it take before 90% of taxpayers have been sent their refunds, okay? So the way the curve is done, this half right here is 0.5 or 50%, okay? And the right-hand side right here is another 0.5 or 50%. Okay, since this is perfectly normally distributed, we know right here from our problem. So we want to know how long will it take before 90% of taxpayers have been sent their refunds. So if you follow me here, this is 50%, plus we'll add another 40. So this right here is 90% of people, right? So if we have 0.5 and we add 0.4, so sorry, this right here is 90% of people. So we want to know how long will it take before all these people have been sent their refunds. So is it going to be the tail end right here or this portion right here, right? Now you have to think about this logically. It can't be on the left-hand side because anywhere within the left-hand side, it could be 80% of people, 70% of people, 60% of people. Only once we pass this threshold right here will all 90% of people have received their tax refunds. So we know just by that what we're looking for is the tail end right here, right? So knowing that, what we're trying to isolate for is how many weeks will that take, okay? So we're going to follow the same steps as before, simply we're isolating for something different. And what I mean by that is we know that our formula is z equals x minus mean divided by the standard deviation, right? So what do we have here? We have the probability that'll lead us to determining the z at this point right here, okay? Do you remember when we covered the theory? I told you guys that for each x, there is a z at the same point. So this is the z that I want, and the z's are represented by the probabilities that stem from the mean. So from the mean to the right or from the mean to the left, that's how you determine the z that corresponds to the probability right here, right? So what I'm going to do is in the z table, I'm going to try to find the closest value to a probability of 0.4. And that represents a probability of of 1.28. So that represents a z of 1.28 is the closest to a probability of 0.4. So then going back to my formula, I have my z, 1.28. And once again, I can't stress enough where it becomes important to put the negative signs, because when you're isolating for an x, if you have a positive z as opposed to a negative z, it's going to change the value of your x, okay? So then what we're looking for is the x. You always have only one unknown, so we'll fill in for everything else. So solving for x is going to equal a total of 15.84 weeks, okay? So these are a little bit different, these problems. You really have to take it one step at a time. So knowing that each side of the curve is 0.5, as you read out the problem, really draw it out, okay? So we know that this is 0.5, 0.4. Right here at this point, we will reach 90% of taxpayers. And how long will it take before 90% of taxpayers have been sent their refund? So we know that we need to cross this threshold for 90% of taxpayers to receive their refund. And so what we want to know is the z-score at this particular threshold, which is a z-score of 1.28. And that gives us an x of 15.84 weeks. So 90% of taxpayers will have received their refund at 15.84 weeks, okay? Which means that we need this probability right here because the z's are always in relationship to the mean. Remember that. All right, so that concludes the review part 2 for the Comm to 15 midterm. Best of luck, everyone, and thank you once again for your continued support.